Okay. So here the question's a bit cut off, but I'll add to it. So here's our equation for conversion of carbon dioxide with potassium peroxide. Which we will need at some point. So this takes in carbon dioxide and gives oxygen. I'm just going to scroll this down a bit. Okay, so now the question is if we are creating air at a rate of 3 liters per minute, and our CO2 is 0.034 of air. So that means that for our CO2, we are creating 0.034 times 3.0 liters per minute. Okay. And then the question asks, how much potassium peroxide in grams do we need for a 5-day trip? And so, yeah, I think that's enough to solve the question. So in a 5-day trip, we need to know our volume of CO2. And so that's going to be our rate of CO2 production. I'm going to just solve this through. So if we put this through our calculator, then we're producing 0.102 liters per minute. And so our total volume in 5 days is going to be 0.102 liters per minute times 60 minutes per hour times 24 hours per day times 5 days. So our days will cancel, our hours will cancel, and the minutes will cancel, leaving us with an answer in liters. And so this gives us 734.4 liters. And now, given a volume of CO2, all right, now I remember what else is in the question. So the other stuff given in the question is that our ideal gas constant is 62.363 millimeters of mercury, liters per mole Kelvin. Our temperature is 250 Kelvin, which is extremely cold. It's like negative 20-some degrees, but okay. And our pressure is 728 millimeters of mercury. So now with the ideal gas law, we can solve for the number of moles of CO2 that this involves. So we can rearrange and say that our number of moles is PV over RT, which is 728 millimeters mercury. Our volume that we computed above, which is 734.4 liters, over our gas constant, which is 62.363 in our appropriate units, and our temperature, which is 250 Kelvin. Alright, so then that cancels, and that cancels, and that will flip up to the top to give us an answer in moles, so that looks good. If we run this through our calculator, we get 34.292 moles. And now, if we look at our balanced chemical equation above, we can see that our potassium peroxide and our carbon dioxide are in a 2-to-2 ratio, which is another way of saying a 1-to-1 ratio. So we have a K2O2 to CO2 ratio of 1-to-1. So that means our number of moles of K2O2 is just equal to 34.292. So if we have this many moles of carbon dioxide, we need an identical amount of moles of potassium peroxide. So to get mass in grams, we need our molar mass. So mass of potassium is 39.0983. Mass of oxygen, or molar mass of oxygen, is 15.9994. And so our molar mass for potassium peroxide is 2 times 39.0983 plus 2 times 15.9994, which comes out to be 110.1954. Okay, and so we have our moles, we have our molar mass, so that means our mass of K2O2 is just our moles times our molar mass, which comes out to be 34.292 moles times 110.1954, which when we run this through our calculator is 3778.82 grams. Or we're given 2 significant figures on our production of air, and so that would just be 3.8 times 10 to the 3 grams. And so that would be our mass of potassium peroxide in grams. So we need PV equals nRT to get the volume. Solving this through. So our gas constant wasn't given in any particular units, so you can use whichever units you want. They converted to atmospheres, which is fine. 34.30 is what they got for their moles, which could be the case for rounding. And depending on rounding errors and how you define your molar mass, the mass in grams comes out to be 377986 for them. A little different, probably due to just definitions of molar mass, but if we round it to 2 significant figures, the 2 answers will be the same. So I'd say the solution is correct. It would only differ in some rounding places.